Hello YouTube, this is Dazzathecameraman. Today is July 29th, Saturday, New Zealand time, and I'm pleased to have with me Scott and, I'm pleased to have with me Eric and Chris, who are both astronomers. Welcome along, Eric and Chris.
Thank you for having us.
Thank you.
Thank you. So Eric and Chris are both astronomers, and I'll let them give a bit of an introduction about their work and their qualifications, and we'll cover some topics, including the upcoming eclipse, total solar eclipse on August 21st, which is next month, which will be visible across the USA. Go ahead, guys.
Let's start with you, Chris.
I'm Chris. So, yep, I study astronomy. And my focus is on exoplanets, actually. But this summer, we're both working on a project studying variable stars. Did we just lose video? I'll keep going.
I think you lost video to improve sound quality.
Okay. Anyway, this summer, we're both working on a project to study variable stars. Eric's doing it for
basically a thesis project.
And I am doing it as an excuse to write some software for automating our observatory.
And so just to take that a step further, the specific stars we study are Cepheid variable stars, specifically in the constellation of Cygnus. We have about 10 stars we look at, and we're looking at a specific type of variable star, Cepheid variables, alpha 2 Cepheids and delta Scuti Cepheids. And the two types of particular interest to us are the delta Scuti, because they have a short period, 8-hour period, the particular star that we're looking at, V819 Sig, which allows us to get a lot of data in one night. And then the other type, the alpha 2 Cepheid variables, have unknown periods. So the reason those are of particular interest to us is because since the periods are unknown, we can actually determine those periods via our observations and publish that data. And so it's original research. And the inspiration for it was to reproduce Edwin Hubble's research, where he used the distance luminosity relationship or period luminosity relationship of Cepheid variables to determine distances in the universe. And it's one rung on the cosmic distance ladder, which is a term astronomers use to certain objects that determine distances. Like Cepheid variables are one step on that cosmic distance ladder. A type 1a supernova would be another, and so on and so forth. So our qualifications are: I'm currently an instructor, university level, intro physics laboratory, experimental physics lab. I teach that for non-physics majors, but I specialize in astronomy, observational astronomy, and astrophysics. So that's just a little bit about our qualifications. So, and we're glad to be here to discuss the upcoming solar eclipse.
Right. Well, thank you for joining me, and thank you for that introduction. Now, Eric, I understand you are qualified as an astrophysicist. Am I correct on that?
Yeah, well, technically it would be physics with a minor in astronomy, but that's the degree, what the degree is. Yeah, astrophysics is basically what I specialize in, yes. But if you want to get technical about it, it'd be physics with a minor in astronomy.
Right. Okay. Now, in case anybody's wondering, I've turned off my camera because the audio for me is quite choppy, so I'm having problems with the streaming. So I'll just go with my microphone at this stage, and I'll present Eric and Chris to everyone. Now, so we've got this eclipse coming up next month. Actually, I'll just swap screens for a moment, and this was something that I shared earlier, which is the website Shadow and Substance by my friend Larry, who was hoping to join me earlier. Unfortunately, he had to cancel. And as we can see, he has produced these animations of the eclipse timings as the shadow of the moon passes across the United States on August 21st. and we can see some timings down there. And as we scroll down, there's a list there that you can click on the different states, locations, and check the timings and the percentage of the eclipse from each one of these locations. Now, this is interesting to me because it just goes to show the sort of calculations and predictions that are involved in eclipses, particularly solar eclipses, where you have such a defined shadow passing across the Earth. And so there's a couple of points that comes out of this for me, is that the ability to make these sort of predictions well ahead of time. And I'm hoping that you can speak into the length of time ahead of time that these predictions can be made, and have been made, in fact, and also the sort of calculations that are involved. Obviously, without getting too technical, this is way beyond my mathematical abilities, and I'm sure that most people watching are probably in the same boat as me. So maybe if you can talk about the length of periods that are involved in these predictions, how far ahead that we can actually make these predictions for eclipses, and we could go from there.
Sure. Well, I guess the best place to start is at the very beginning. So eclipses were first predicted by the Babylonians, solar eclipses, but they're very difficult because you know, the Earth's only the shadow that the sun leaves on the Earth, the moon on the Earth, is only a few tens of miles across, and so it's hard. It was really hard for them to get accuracy as far as dates go and positions. But the first recordings of solar eclipse predictions were the Babylonians. Now, when the first accurate predictions were made by the Greek Thales around 610 BC, and I'm sorry if I'm butchering his name. I have a hard time pronouncing those Greek names. So he was actually one of the first to predict them with a fair degree of accuracy. Now, he was able to predict them to the year, and he was able to do that years in advance to the year using a specific method. I forget the name of the method. Was it sonar method, or what was the name of the method we were looking at earlier?
Are you talking about the Saros?
Saros, yeah, using the Saros, where a previous eclipse happened, and he was able to use the timing and positioning of the previous eclipse to predict the following eclipse, which happened a year or two later. That accuracy stayed about the same until the time of Ptolemy, and during that period of time, then they were able to predict eclipses further in advance, years in advance, in fact. And they would have the accuracy down to within the months. They still couldn't get it down to the exact day. Now, let's fast forward 2,000 years to where we're at today. And now using modern computers and custom written software, which is how solar eclipses are predicted now, using the same software that is used in planetariums, such as like the Griffith Planetarium or the Hayden Planetarium, or even the planetarium they have at the institution where we're at. You can predict eclipses thousands of years out, and because of once the basic mathematical formulae are programmed into the computer does the rest of the work. Now, for you to do that by hand, it'd be very difficult to do that, you know, just using a calculator and pen and paper. Even for an astrophysicist or an astronomer, there's a lot of calculations you have to take into account. You have to take into the diameter of the moon, the diameter of the sun, the distance of the moon and the sun, and where the sun is at in relation to the ecliptic plane. So there's a lot of variables that go into predicting solar eclipses. As far as the 2017 eclipse goes, I don't know the exact date, but a good resource to look at that would be NASA, because I believe NASA is the first to predict the 2017 eclipse. In fact, I was looking a little bit over NASA's website earlier, and I believe they were the first to predict the 2017 eclipse. And if I remember correctly, I believe it was in the 70s when they knew of the first these eclipses. They predicted the ones in 88, I believe. 92, and I may be a year or two off, so you have to take these dates with a grain of salt. I'm not giving exact dates, just those regions. But as far as North America is concerned, there's one in 88, 92, I believe 97, and then the Great North American Eclipse is what they're referring to, the one coming up on August 21st. So those were predicted in the early to late 70s by NASA. So
it's important to
right. So I'll just pick up on that point. So this eclipse was predicted back in the 1970s, and we've got these very detailed predictions for the timings. We can see the path of the eclipse sweeping across the United States, and there are some people who are claiming that there is a brown dwarf within our solar system, in fact, very near to the sun, so within our inner solar system. So what sort of effect would an object the size and, more importantly, the mass of a brown dwarf have on events like this?
Oh, well, that's a great question. Let me ponder this for a second. For one, the mass of a brown dwarf would have an enormous impact on our solar system. Brown dwarfs are typically 10 to 13 Jupiter masses. So imagine having an object this 10 times the size of Jupiter in the inner solar system. That would, and here's a cool way to actually verify this for some of the viewers out there. You can do what's called a PhET simulation, which is a simulation of how solar systems or basically gravitational orbits work. And there's a great PhET simulation by the University of Colorado. Just Google solar system PhET simulation, and that's PhET, P-H-E-T. And you can build your own solar system. You could put an object within between Earth's and the sun's orbit that is 10 masses of the sun, and your viewers can see what would happen. It is very well known what large objects, what kind of effect that they will have within a solar system. These are based on Newton's laws of gravitation, where the gravitational force is equal to gravity times the mass of one object times the mass of the other object divided by the radius squared. I mean, it's a very basic equation that has been around since the time of Newton. And we've refined that. There's certain permutations on that increase accuracy. But the effect that a brown dwarf would have on the eclipse, well, you want to add to that, Chris?
Sure. We mentioned earlier how the ancient Babylonians estimated the dates for eclipses. We call that the Saros cycle. And what that is it's a very regular 18-year period between two eclipses. So this eclipse that's coming up in, next month, there's going to be another one in the same spot, well, the same alignment with the Earth, Moon, and the Sun, about 18 years from now. And that's very steady. They noticed that just by tracking where the eclipses would fall in the calendars. And over the course of hundreds of years, they got to recognize that pattern very well. So that was the way that they first started to estimate these dates. That's still there today, and we still have that same cycle even thousands of years later. If there was a large mass object going through the inner solar system, that balance of gravity that lends itself to having such a regular cycle like that wouldn't exist. There's just no way. I mean, you'd have this mass with this huge amount of gravity interacting with not just the Earth, but the Moon. I mean, just imagine what the Moon's orbit would be like if you had something massive like that passing by every so often. You wouldn't have that regular orbit going through there.
And additionally, I'd like to add to that. When two bodies orbit each other, especially large bodies, say like an object the size of a brown dwarf that close to the sun within Earth's orbit, would have a large gravitational effect on the sun. And as an astronomer, we would see that gravitational effect through a process called radial velocity. So as two objects orbit each other, they tug at each other as they orbit a center of mass. So this technique that I referred to, radial velocity, is kind of like, what's a good analogy? It would be the Doppler shift. How the Doppler shift when a car, like an ambulance or a police car or a fire engine drives by you, you hear a high pitch as it's coming close to you, like nee, 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 and as it passes, it goes the pitch drops. Well, that same effect happens with light, and we call that redshift and blue shift. And so if there was a large body orbiting the sun, for one, we would see that effect via radial velocity coming from the sun. And there are many astronomers across the world that professionally do radial velocity. In fact, some of my colleagues do. They detect radio planets using the radial velocity method. And there's been no detection of the types of radial velocity that would be present if a large body like a brown dwarf would be orbiting in the inner solar system. And as Chris said, we would. I agree completely with him. We wouldn't have these regular 18-year cycles of the eclipse based on the Soros method or cycle.
Right. Now, a couple of people have made comments in the chat asking, so why are the planets being perturbed then? As far as I'm aware, there is no evidence that the planets are being perturbed. What is your take on that, please?
Well, at this, yeah, none of the planets are being perturbed. Now, with the exception of, for full disclosure, there is, Caltech has put out a paper stating that, in the outer solar system, there are slight perturbations in Uranus, but that could be created by any, a trans-Neptunian object in the Kuiper Belt, which is in the Kuiper Belt is in the far reaches of the solar system, and the type of perturbations they're saying are nowhere near the type that would be indicative of a brown dwarf star. This is more like a small dwarf planet. And there are many dwarf planets in the Kuiper Belt. You have Makemake, Haumea, Sedna. So as far as perturbations go, other than the ones you find in Uranus and Neptune due to trans-Neptunian objects, which are well known in astronomical circles, there are none whatsoever in the inner solar system, or in fact even out to Jupiter or Saturn.
Right, and go ahead.
Say if there was something that was 40 or 50 times Jupiter's mass in the inner solar system, the kinds of perturbations that you'd be seeing, you wouldn't need math to figure it out.
Yeah. We would know it. It would be hellfire and brimstone on Earth. I mean, we would really, wow. our Earth cycles or weather would be extreme. I mean, the moon would be pulled out of its orbit. The Earth would be pulled in closer to that object. Mars, in fact, would be, the entire solar system would be unstable. And like I said, your viewers can run their own simulations using Universe Sandbox if they want to spend a couple of bucks. That's a really good solar system gravitational simulation. But if they just want to do it for free, it's very simple. Just PHET simulation. University of Colorado solar system, and they can make their own solar system and see how gravity works and interacts in our solar system with other bodies.
Yeah, those simulations are really good, but the kinds of people that I'm assuming are really getting into the brown dwarf idea probably are going to want to look at the underlying math behind that. And I know that might be a scary thing to get into, but a lot of the math is actually not that complicated, at least if you're talking about two bodies. Once you start to introduce 3 or 4 or 5, then it gets pretty crazy. But like we were talking about earlier, some of those gravity equations are pretty simple.
I can draw one on the board real quick on the back here so you guys can actually see.
And you can actually start to see what kind of energies would be involved if you have objects of that mass that close to the Earth. So,
can you see this here? That coming up on the screen? We might have to come a little closer.
Do that.
Yeah. So just to explain this this equation here, so the force that's caused, the force that you would get from two orbiting bodies is equal to the gravitational constant, which the gravitational constant is just a number, and that number is forget off the top of my head. 6.6. Yeah, 6.67 10 to the minus 11, and I believe that's newtons per kilograms meters squared or meters squared. I always look up my constants, but this is just a constant. the gravitational constant. And then you have mass 1, say we call mass 1 the sun, and mass 2, let's just call it this hypothetical brown dwarf. So if any of your viewers were so inclined as to find out the type of forces that would be experienced from those types of 2 orbiting bodies, you can look up the sun's mass in kilograms and look up the brown dwarf's mass in kilograms, which would just be a simple conversion. The brown dwarf's mass, typically brown dwarfs are 10 to 13 masses of Jupiter. And what's that? Well, they vary, but the base levels are 10 to 13. And the sun is, look that up on Google in kilograms, multiply those by each other, divide them by whatever radius or distance, I should call this D for distance, distance apart, and multiply it by this constant here, and then that'll give you your force of gravitation, or the force due to gravitation of those 2 orbiting bodies. So those FESS simulations are based on very simple equations when you have 1, 2, or 3 orbiting bodies. They get more complicated when you add planets in, more than 3 or 4. But this is what it's based on. If they were so inclined to do the math themselves, it's very simple. I mean, this is no greater than high school level math. You have some multiplication and division and 1 squared number. So those simulations aren't just they don't come out of they don't come out of anywhere. I mean, there's mathematical equations behind them that are based on universal laws of gravitation. So just to give them, a little food for thought, or if they want to give it a try themselves. And if any of the viewers are able to write in any computer programs, you could fairly easily design one yourself using that mathematical equation. So.
Okay, Chris, did you want to add anything to that?
No, it's pretty good. I always recommend that people don't just take other people's words for it. Look at it themselves, and like you said, the math is pretty simple.
Agreed. Don't take our words for it. Do your research and do the math yourself, and you'll come to the same conclusion.
Right. Now, just to recap a little bit, talking about the claim that the orbits of the planets were being perturbed, and you mentioned that trans-Neptunian objects and so on. So as far as the planets in the inner solar system, there is no evidence of any perturbation of the planets. Certainly nothing that you would notice in the sky. For example, if you were using an old GO2 telescope that had never been updated online, and you had it correctly aligned and all the rest of it, and then you selected GO2 to find, say, Saturn or Jupiter, you would expect that the telescope being correctly aligned would still correctly find those planets at the given right ascension and declination coordinates in that database.
Yeah, and it does. I, in fact, had a telescope out last night. I had a 8-inch Celestron twin out last night using the GO2 method. I did a 2-star alignment. I aligned on Arcturus and Deneb. And the people that I was presenting for wanted to look at Saturn, and we had Saturn in the telescope for about an hour and a half, and the alignment was immaculate. I did not have to realign the telescope. It followed Saturn the whole way. We looked at other objects. Well, we were able to look at Jupiter for about 15 minutes before it set. Where we're at, Jupiter's setting a little early right now. Well, that's wherever in the northern hemisphere. So yeah, and we had no alignment issues whatsoever. And this is, a cheap, well, not cheap, but fairly inexpensive, telescope that ranges from about $1,700 to $2,500. But even if you had your very basic Celestron or Meade or any brand of telescope with the GO2 function, with the software that tracks, yeah, you'd be able to track for hours without having to realign. And I've done so myself.
You can do it with a unmotorized mount too. If you have an equatorial mount, just point it at Polaris and look up coordinates. A lot of equatorial mounts are going to have the right ascension and declination notated on the axes. I mean, you could, even one from 50, 60, 70 years ago, you could just align it on Polaris and you can use those and it'll be very reliable. You'll still get pretty much where you want to go.
Which actually brings up,
right.
kind of a side thought that I had. I know that there are a lot of claims. Some claim that there is a brown dwarf in our solar system, and I propose a challenge to provide me with the right ascension and declination of this, and I can take a 16-inch Meade LX2000 or LX200. I'm sorry. Schmidt Cassegrain telescope, research grade with a CCD camera on it, and I will look at those coordinates and gladly show the results that I find. So if anybody out there knows the right ascension and declination of this object, or if they're more familiar with altitude azimuth, I can work with that too. If you provide me with some coordinates, I'd be more than happy to look at that area of the sky. Right, Chris?
Absolutely. And this is a challenge that I frequently put it out there, because people tell me all the time that Nibiru or Planet X or a brown dwarf is real, and that it's currently within our solar system. Mm-hmm. And when I say within our solar system, I'm talking this side of Neptune. Oh. And I challenge them and say, well, you provide the right ascension and declination coordinates, and me and my astronomy colleagues will point our telescopes at those coordinates, and we'll see if we can image it. Now, some people think that infrared telescopes are only available to NASA and the government and so on. And of course, this isn't true. Our good friend Astronomy Live also has his own infrared camera, and I'm sure that you guys are using infrared as well. Is that correct?
You don't. Well,
we have the equipment, but we don't personally use it for our research.
And the whole infrared thing is kind of misleading anyway, because if there was an object like that within our solar system, like you said, within the orbit of Neptune, it wouldn't matter.
Yeah, right.
It would be bright enough, even a brown dwarf. Think about how bright Jupiter is. And Jupiter is one of the objects in the night sky. Mm-hmm. Even if you put it out to the distance of Neptune, it's going to be very bright. Mm-hmm. Through a telescope, there's no missing it. You don't need an IR filter for that.
Right. I mean, we look at objects, well,
12, 13th magnitude.
Yeah. I mean, the limit of our research grade telescope is the far limits. I've been told are 16th magnitude, but I think that being a little conservative, I would agree with Chris that the 13th, 14th magnitude is about the limit of our instrumentations that we use where we're associated. So it'd be very easy to see. And in fact, you don't, like, if a brown dwarf was that close to the solar system, you wouldn't, like Chris said, you wouldn't need an infrared telescope. A brown dwarf would be visible in the visible spectrum. It just wouldn't be you don't see the different colors of brown dwarfs unless you're looking in the infrared. Then you can make out the different colors, but it would appear magenta, I believe, off the top of my head. Again, brown dwarfs aren't my specialty, but
just white.
We would see it. It would just be like Jupiter in the night sky, only brighter because of the size and the mass. So more surface area to reflect light.
Right. Just in response to a comment that's just been made in the chat, before I read the comment, can you tell me what the mass of a brown dwarf would be compared to Jupiter?
Oh, they vary. I've read, Chris and I were just talking about this on the side. I've read that brown dwarfs vary from bare minimum of 10 to 13 Jupiter masses, but anywhere upwards to like 40 Jupiter masses. Right. And I've read similar figures. I think 13 through to 75 to 80, I think I read. Yeah, and that's fair. I mean, when you're speaking in astronomical terms, order of magnitudes are how we measure things. So. Right. So that the comment that was made in the chat was that Jupiter is a brown dwarf. Well, obviously, if the minimum mass for a brown dwarf was even 10 Jupiter masses, then clearly Jupiter cannot be a brown dwarf.
And we've found planets that are larger than Jupiter in other solar systems.
Yeah, hot Jupiters is what we refer to them as, and that's one of the first exoplanets that were detected. The types of exoplanets are referred to as hot Jupiters, and they're in the inner solar system of their respective around their respective parent star, and their masses are upwards of what's some of the larger end hot Jupiters? 34, yeah, yeah.
So there's definitely more of a spectrum between different types of planets than going up into stars.
Yeah, and just because the mass is up there, I mean, like Chris said, you can have the masses 30 times the mass of Jupiter, and it doesn't mean that it's going to be a star. Yeah, I mean, you need the right fusionable material in there, and to sustain a nuclear fusion to produce the star. I mean, so.
Right, now you mentioned a very good point, and this is one I've also brought out many times before as well, is that if there was a brown dwarf within our solar system, certainly within the orbit of Neptune, it would be very easy to see in visible light. You would not need infrared to see it. And we can all see Mercury, Venus, Mars, Jupiter, and Saturn with our naked eyes. We can see Uranus and Neptune in visible light. We don't need to use infrared to image them through a telescope. You can use an ordinary optical telescope to image them. I have also imaged Pluto through a 14-inch telescope in visible light. I didn't have to use infrared. Now, we mentioned, or we sort of touched on Planet 9 earlier, and the research done by Brown and Batterton at Caltech, and their theoretical, let me just kill my phone, sorry about that. Their theoretical object is, they say, according to their calculations, would come no closer than 200 AU to our sun. And by comparison, Neptune is 30 AU away from our sun. So we're talking considerably further away than Neptune. So all these people that are posting photos and videos supposedly showing Nibiru, Planet X, a brown dwarf, or even Planet 9 as they think that Planet 9 is Nibiru, Planet X, obviously they're dreaming. And we're seeing lens flares and reflections and all that sort of thing. You also mentioned Polaris, which is a very good point, and again something that I always point out, that people claim that the orbits have been perturbed and so forth, is that Polaris is still our pole star. So if the Earth has been affected and pulled out of its orbit and knocked off its tilt, as some people are saying, they claim that the sun is rising and setting in the wrong place and all the rest of it, then Polaris would no longer be where it is and where it should be. Now, I should point out again that Polaris is not exactly on the North Celestial Pole. It's approximately 2/3 of 1 degree from the North Celestial Pole. So this is why whenever you see a time-lapse star trail image, you'll see that Polaris actually scribes a little circle around the North Celestial Pole. So, and again, you touched on aligning the telescopes using Polaris. And again, that this is proof that the Earth and the planets are exactly where they should be in their orbits.
That is correct. Yeah, that is correct. Yeah, that is.
I also want to mention rising and setting along. We just updated some of the software that we use to guide some of our telescopes, and one of the things that we started using was aligning just on a single solar system object. If you're in a hurry and don't want to do the whole polar alignment with Polaris, or even just do a 2-star alignment. Like for instance, if you just want to observe the sun, all you have to do is put the telescope on the sun. This is pretty easy to find, and just tell the telescope software that that's what you're looking at, and it will do a very good job of tracking it. And this is software that was written years and years ago, and it's, you know, I fully expect that software to work for the next several years until we get around to updating. So if the sun was setting and rising in different places than it should be, then that would fail very quickly.
Right, absolutely. Now, there were some very good questions further up. I'm just going to, I don't know if you guys can see the chat there. I've sent a link to the chat box in our Hangout chat. Hopefully that'll bring it up for you if you haven't got it already.
You could do that. That would be nice.
Let's try and get over here.
Yeah, try to pull it up on the other laptop. Well, we're going to pull up the chat group so we can look at the questions also.
Right. So one of the questions was, can you explain the difference between a brown dwarf and a brown dwarf star? Is there a difference?
No.
Not that I know of.
Brown dwarf it's just a brown dwarf star. Yeah. They're the same thing.
Same object.
Right. I think some people have said that a brown dwarf is not a star, and therefore it can't be called a brown dwarf star.
Yes, exactly.
What's your response to that?
A brown, that's exactly right. You know, whether someone calls it a brown dwarf or a brown dwarf star, it's referring to the same object, and it's a substellar mass object between a gas giant planet like Jupiter and I guess the next smallest star that's actually undergoing fusion would be a red dwarf, I think.
Right, red dwarf.
So it's there's a limit, a lower limit to a star's mass where that star can actually undergo well, a certain type of hydrogen fusion. Still fuse deuterium, but that's going to end very quickly in its life. It's not something that's going to really affect what we're looking at in the night sky. So yeah, technically, I would say a brown dwarf isn't a star, but it's just
technically no.
It's just one of those terms that gets thrown around to the point where everyone uses it, even if it's technically wrong.
Yeah, there's no sustained fusion within a brown dwarf, but you know there was initial chain reaction that wasn't sustained, and then you were left with brown dwarf.
Yeah, and one of our colleagues pointed out that the definition of a star is an object that's undergoing a sustained fusion reaction.
Yes,
it's not not something that did for a little while.
Yeah, fired up and then turned off, and so technically it's that's just wordplay, right? Mincing words.
Right. Okay. I'm just scrolling through the chat. There were some very good questions there. I'm just trying to find them there. Okay. Stephen James asked, does anyone know when the last surprise, in quotation marks, surprise or unpredicted eclipse occurred? Is that now inconceivable with modern astronomy? If so, why?
I've never heard of a surprise eclipse in the years that I've been doing this. In fact, I don't know that in modern times there have been.
I don't know how you would either. The motion of the moon around the Earth, the motion of the Earth around the sun is
very stable,
pretty consistent at this
point. Yes, and that's why in planetariums you can go back to when I give planetarium shows, I demonstrate the precession of the equinox, which is 25,000 years, and I can go back multiple precessions, either into the future or into the past. So we're talking, I can demonstrate, what the stars looked like upwards of 75 to 100,000 years ago. And so our orbits are so stable that we can do so. So there being an unpredicted eclipse that's something I've never heard of.
That's certainly something I've never heard of either. And the only thing that I can think of is that maybe this is reference to some events that seemingly have no other explanation. Maybe even referring to biblical accounts such as, was it 6 hours of darkness, I think it was, when Jesus was crucified, or something like that. Right. And that was around the Passover, which would have been a full moon. So it certainly could not have possibly been a solar eclipse caused by the moon on that event. Now, there's another question here, and I know absolutely nothing about this, so I hope you guys can speak into this. If time allows, this is from Data Junkie. I'd be interested to hear why they think the Schumann resonance has had such wide fluctuations of late. Do you know anything about Schumann resonance?
I do know a little bit. Again, that's not my area of expertise. I knew the Schumann resonance is the frequency at which the Earth vibrates or resonates at. Could you repeat that question one more time? I just want to ponder that a minute.
I'd like to hear why they think the Schumann resonance has had such wide fluctuations of late.
Wide fluctuations of light.
Late.
Oh, at late. Oh, I'm sorry. I'm sorry.
It's my accent.
Sorry. I am not aware of any fluctuations in the Schumann resonance, nor have I heard of anything within the physics community. And again, this is not my area of expertise, so I would kind of be speaking out of school if I was to try to explain anything to that effect. I wish I could speak more on that. Chris, is there anything that you could add to that, or?
Atmospheric physics is definitely not my area of expertise.
Yeah, and I don't want to speak to anything that I don't know
could,
or give false information. I could look something up on the internet, you know, or out of one of our textbooks about the Schumann resonance, but I feel like your viewer could do the same. I don't know.
I could make some
Sure,
wild guesses. It would be entertaining.
Yeah, well, yeah, and of course, you know, that's the last thing that we want to do is to go down the road and pretend that we're experts in areas that we're not. Right. And I mean, I guess this is the reason why we're doing this Hangout too, is that we're debunking the channels that actually do that. You've got people who know absolutely nothing about astronomy, who wouldn't know one end of a telescope from another, sure. Claiming to tell the YouTube community all about what's going on in the solar system. And they have no expertise in what they're talking about. And this is where you get yourself into trouble, of course, when you start talking about things that you actually know nothing about. So, you know, it's always better to say, well, I don't know. I'd have to go away and research that and come back to you with an answer. So,
agreed. Agreed.
You don't know is a good.
Yeah, that's one of the best. If we knew everything, we'd be out of a job.
Yeah. Okay, I'm just searching through the chat. I don't know if you guys have spotted any questions that you want to respond to there.
We're still working on pulling it up on our other laptop.
I was trying to do it without actually joining.
Yeah, Chris is working on that right now. But if you don't mind fielding the questions for us, we'll answer until we get them up.
Okay. If anybody wants to ask a specific question, could you please include Dazzathecameraman, all one word, in the chat, so that will highlight for me and I will see your question more easily. Okay, what I'm going to do, I'm going to go back and share my other screen again, where we're looking at the Eclipse animation. And there was a question earlier, much earlier in the chat. Very good question. Now, we know that the sun rises in the east and crosses over and sets in the west. So the question was, why are we seeing the shadow moving from west to east in this animation? And some people are a little bit confused about that. Would you like to explain that for us?
Yeah, let me think about this, put my three-dimensional thinking cap on so I can explain this. So as the Earth rotates and the moon passes in front of us, the shadow would move. So it has to do with the, so if the sun is rising, sorry, I'm just thinking about this. I like to try to think about it before I answer because it's three-dimensional. I'm trying to get the picture in my mind. So as the Earth rotates.
Well, before you answer, how about I play this other animation, and it might actually help to make the situation clear. So,
oh, that would be great. Yes.
Yep. So again, this is from Larry's website, Shadow and Substance. And you can see that the Earth is turning from west to east, and the moon is also moving from west to east as it orbits the Earth. And I think that is the key to the motion. Of course, the Earth takes approximately 1 month to, did I say the Earth? The moon takes approximately 1 month to orbit the Earth. And I think this is the motion that we're seeing across here, if I'm correct.
That is exactly correct. In fact, that's what I was trying to visualize in my mind, is that put the Earth, the moon, and our rotation around the sun into perspective. And you know, and then sometimes that's more difficult than one would think, trying to visualize our motion through the solar system, you know, in your head, trying to put together that three-dimensional spatial representation of our solar system and how things work. And even myself, being, you know, astronomer and astrophysicist, I ponder these things for hours on end. I'll lay in bed at night and try to picture how our Earth orbits the sun in my mind, and how the moon orbits the Earth, and then how the sun orbits the galaxy. And when you're looking at all of those different variables, it's hard to try to mentally represent that, all those motions together. So I mean, it's a nice thought experiment to try to do these things in your head. But people that make videos like this, my hat's off to them, because it really helps visualize the experience.
Right, and thanks again to Larry for these animations. Again, that's on shadowandSubstance.com if you want to go and check out those animations. And as we scroll up, you can see that there is a list, so you can choose from the different states, locations, and see what sort of view that you would get. For example, from Missouri, here is the view, and gives you the percentage of totality there from different locations. So I hope that's cleared that up. As you say, trying to visualize things in 3D can be quite challenging sometimes. And to make things even more difficult, of course, is that when you're like me living in New Zealand down in the southern hemisphere, you've also got another factor to consider is that we're looking at things upside down, basically, from people in the northern hemisphere.
Sure. Well,
so
it's all relative.
When we look,
yeah, we were looking at things upside down up here from your perspective. So
yeah, so when we look at the constellations in the sky from down here in New Zealand, everything's upside down. Orion is on his head. Scorpio is upside down. And, you know, these are nice, clear, easy to recognize constellations in the sky. And when we have visiting groups coming through the observatory, I'm pointing them out. I'm having to point out that they're actually upside down because we're in the southern hemisphere.
I bet you have a great view of the large and small Magellanic clouds down there, though. That is on my bucket list, is go down and see those.
Yes, we certainly do. But also, I've never seen the Andromeda Galaxy, and at certain times of the year it is quite low down just above our northern horizon, and that's on my list of things to do. If I remember correctly, I think it's in December that I would have to check. I'd have to double check on that, but well, I'm hoping to try.
It's pretty high right now. It would be about December.
Right.
Yeah.
Yep. So I'm hoping to photograph that sometime, and that would be a good one to add to my collection.
Absolutely.
Okay, I'm just putting you guys back on screen here.
That's a great website, by the way, that you just showed. I'm going to have to take a look at that when we're done with the Hangout. Kudos to whoever wrote that. It's a beautiful website.
Yes, he's also got a YouTube and Vimeo channel as well with a number of his productions on it. So well worth checking out.
Yeah, I'll definitely do that. I'm impressed. I really was pleased to see that animation, and his Eclipse animation is really neat.
Okay, I've just been notified in the chat that my audio is too loud. Are other people finding that? Just let me know in the chat and I'll adjust the levels if I need to. Okay, are there any other points that we want to cover? I don't know if you've got the chat up now.
Were you able to pull it up, Chris? I think.
No, I think
we're having issues pulling it up. We tried to join on the other computer, and oh yeah, go ahead. You take over.
Okay, I did send the link to the pop-out chat in the Hangout chat. Did you see that there?
Right here.
Yeah, I'm getting it. There we go. Got it.
Oh, we can split screen the two.
Yeah, I split them into windows so I can see both the Hangout and the chat at the same time.
Yep. We're getting it.
Moons of Jupiter is a good point too. Elvis Velez has just mentioned moons of Jupiter, and again, you know, I've got a piece of very dumb software on my computer that I bought back in 2011 called I can't even remember what it's called actually. I remember the Bar Caroller was using it in his planetary alignment watch videos originally. And unfortunately for him, he didn't have the scale set correctly. So all the orbits of the planets were set so they were evenly spaced instead of to scale. and I downloaded this piece of software that he was using so that I could use it in my videos to demonstrate what he was doing wrong. But that program, if you buy the Pro version, which I think costs about $10 or $15, you can view the moons of Jupiter, or the Galilean moons, the 4 main moons, and this program is never updated. You know, it's just as it was today, as when I downloaded it in 2011 or 2012, whenever it was. And I can use that piece of software that's never updated and pull up the positions of the moons of Jupiter and go outside and look through my telescope, and it will show me exactly as shown in the software animation. It will match my view of the moons of Jupiter, which again proves that the planets and the moons and everything are exactly as they should be.
Yeah, the Galilean moons are another great example of why it's so unlikely that a large mass object can be just traveling right through the solar system without pretty crazy effects being seen, because the Galilean moons are all in well, most of them are in a orbital resonance with each other. And it's a pretty delicate balance, actually. If you had a large object passing through every once in a while, it would totally mess that up. So, you know, Io, for instance, might not even be there. It's kind of slowly getting torn apart getting tugged between Jupiter and Europa and Ganymede or Callisto. I always forget what the other one is, but either way, if it's in the resonance. But either way, you know, you wouldn't see those kinds of interactions with something like that when looking by. So.
And there's 67 moons, Jupiter's moons at least. I just seeing that in the chat go by. 67. So.
It's just funny because we've actually been arguing about
it is up for debate. There you'll find different numbers at different places. There's 67 somewhere, 69 other technicals. So
yeah, well, just recently, I've been keeping up with this actually, and just a couple of weeks ago, it was announced that a couple more moons had been discovered. So the official count now is 69.
Yep, that's what. Yep, see, 69. Yep, there we go. Yep. That's funny because that's been a running debate in our physics department.
Well, it's more with minor bodies.
Minor bodies,
and
yes.
exactly where the line is between what's a moon and what isn't, and it's a really interesting area of debate. So
yeah.
Right. Now, Stephen James has just asked, in 2014, Elon Musk said SpaceX would take man to Mars by 2026. Robert Zubrin of Mars Direct proposes we can do Mars within a decade. Is any of this conceivable, or is it just fantasy?
Highly conceivable. Very doable, but we need the type of effort that, in collaboration and funding, that was given during the 1960s to the Apollo missions, or you know, on a collaborative world scale. I mean, it takes a lot of money to put these missions together. So on a government scale, if it's becoming of NASA, you would need almost an act of Congress where we came together as a country and put our minds to going to Mars to get there. I mean, the technology currently exists. It's not an issue of technology. It's an issue of politics, bureaucracy, and funding, which are some of those are the 3 bad words in academia, you know, in physics and astronomy. So it is highly conceivable, but we'll see. It's a matter of money. It's money that's the deciding factor.
Right. Now, of course, it is a long way to Mars, and I seem to recall that the figure for the amount of time to get there would be about 8 months. I don't know if that's accurate or
one way. Yeah, you could do a round trip in about a little over 2 years
with what we have
right now. Yeah,
assuming there's no propulsion developments or anything like that.
Yeah.
And of course, that really comes down to timings of when Mars is coming around to catch up with the Earth in orbit, or rather the other way around.
Every 26 months, a window opens up for the shortest period of travel to Mars. It's about every 26 months we have that short little window. Right now would be the absolute worst time to send something to Mars because it is directly opposite the sun from us. So about 13 months from now, give or take a month, will be the prime window for sending a mission to Mars.
Right. Emmanuel Goldstein, apparently everybody is happy with the audio feed as it is at the moment. It may not be perfect, but hey, if you really have a problem with the quality of the audio, maybe you'd like to donate a new computer for me and we can get it sorted out. How about that? Thank you.
Well done.
Well done, yes.
So moving right along, as I say, everybody seems to be happy with the audio, and if they were all complaining, I'd be doing something about it, but there's only one person that's unhappy. So, okay. So, now, this eclipse on August 21st, as well as testing the timings and so on, which I think is a fantastic opportunity to test the claims that we've got a brown dwarf within our inner solar system, we're going to see if the eclipse starts and finishes exactly as predicted from the different locations. We're going to see whether the path of totality is exactly as predicted across the USA. But the other thing that's going to happen is that the sun is going to be blocked out by the moon. And along that path of totality, it's effectively going to be nighttime during the day with the sun high in the sky. And of course, the sun is still shining behind the moon, and the sun is still shining on anything in the solar system, such as the back side, the far side of the moon, as seen from the Earth. It's still shining on Mercury and Venus and Mars and Jupiter and Saturn and all of the other planets and everything else in our solar system. So if there is a brown dwarf mysteriously lurking within our solar system, then here is a perfect opportunity for us to see it in the daytime sky with the sun blocked out.
You make an excellent point.
Yeah. Now, I remember this has come up before. I remember discussing this with Paul Cox in our live feed with SLU during the 2012 total solar eclipse. And, of course, we didn't see Nibiru. We didn't see a brown dwarf. We didn't see anything that shouldn't be there. I've no doubt that there'll be plenty of videos and photos posted by people claiming to show something that shouldn't be there, because we always see the inevitable lens flares and reflections and even hoaxes, or even other objects such as Venus or Jupiter or whatever. But a brown dwarf within our solar system, when we consider how big and bright Jupiter is, which is so far away, and we consider how big and bright Venus is because of its highly reflective clouds and its locality to the Earth, I think that an object, a brown dwarf, I think they say would be about 4 times the size of the Earth as a minimum diameter. I'm not talking about mass, I'm talking about diameter. So it should be fairly large if it's in the inner solar system, given how big and bright Venus looks. Mm-hmm. So there we go, people. If you've got an opportunity to film the solar eclipse on August 21, I'd be very keen to see your videos and your photos. And one thing that I really kicked myself about not making the most of the opportunity in 2012, even during the partial eclipse that we saw, is the sort of pinhole images that you can get of the sun. So in other words, if you've got a pinhole, or if there's a hole in the curtain or a gap somewhere where the sun is shining through, you're going to get a little pinhole image of the partial eclipse. And one of the things I would have liked to have done was to use a card with multiple pinholes in it to show multiple images of the eclipsed sun. So, and one of the other things too is that we often see these internal lens reflection images that people claim as Nibiru Planet X, and if they did the finger test where they extended their finger out in front of the camera and put it over the object that they believe is Nibiru, they would find that the Nibiru object was actually on their finger. So I've seen last time during the solar eclipse, I actually saw some eclipse-shaped internal lens reflections, or eclipse-shaped Nibiru Planet X, if you like. And again, for anybody that's in the path of the eclipse, if you get the opportunity to take some video with your iPhone in particular, because they do tend to produce these internal lens reflections, then please do the finger test while you're filming, and let's see that eclipse-shaped internal lens reflection over the end of your finger. I'd love to see that.
That'd be interesting. That'd be interesting. You know, it's a pinhole method you brought up. It brings back memories of the first eclipse I ever saw when I was 5 years old, and what we used was a cereal box, and took the cereal box and cut a square out of one side of it, and then you turn your back to the sun, and you put a pinhole on the opposite side of that square in the bottom of the cereal box. And that's an excellent way to look at a partial eclipse, is you look through the square that you cut out in the bottom of the cereal box, and you have the pinhole, or multiple pinholes rather, you know, however you want to do it. And you can look and see the partial eclipse with great detail. And it's a really neat method. It's actually one of my earlier memories. Like I said, I was 4 or 5 years old, and my dad had cut that and readied the cereal box for us. You know, it's very interesting trick to do, and one of the earlier memories I have that got me interested in it, in observational astronomy. But taking that a step further, viewing the eclipse, Chris and I are actually going to be in the path of total eclipse, of totality, and we plan on taking images of that eclipse. We're going to have, well, I'm planning on doing it. I don't know if we'll actually be able to get some images. I'm working on getting a nice camera for that now. We'll definitely have the equipment, telescope, solar filter, all that, and then Chris can speak more about his equipment, but we'd like to, if we do end up getting images of that, we'd be more happy to share that with you and your viewers.
Unfortunately, all of our imaging systems have pretty narrow fields of view, so I can already see the excuses popping up.
Yeah.
That we're only looking right at the sun. We're not looking at things that are more than a few degrees away from it. So.
You bring up a good point.
But they'll still be cool images.
They'll still be cool. I'm more interested in the corona myself, and you know, that's what I'm looking forward to. So.
Yeah, we'll be imaging in hydrogen alpha and visual.
Do you know if we'll be seeing the diamond ring effect with this eclipse?
I don't actually. That's a good question. Probably would be too hard to figure out. Sure, it just depends on the alignment. Let me look that up, maybe. See if I can find it.
Yeah, to be honest, I'm not sure either. I was just looking that up right now.
As I mentioned in the earlier Hangout, with some total solar eclipses, there is something that's referred to as the diamond ring effect. Now, you don't always see this. It depends on how far away the moon is from the Earth, the amount of totality. But sometimes when the moon is the right distance, you actually have this ring of sunlight around the edge of the moon. And you see this little bead of light just as the eclipse is going into 100% eclipse, or just before 100%, and just as it's merging, you see this little bead of sunlight that looks like a gem on a ring, so it looks like a diamond ring.
Yeah, that'd be a spectacular phenomenon to see, you know, with your own eye. I am not sure if we'll be able to see that. I'm looking into that right now.
Well, we'll be able to. So, I think there's two separate things that we're talking about. One of them is the sort of glow of the corona around the sun as it gets blocked by the moon. That we should definitely see. The other thing is the I can't remember the name of it, but they're the bead effect around the surface of the moon. Basically, it's the moon isn't a perfect circle. It's like the Earth. You know, it has surface features. It has canyons and ridges and craters and stuff. And that's going to affect how the light passes around the moon. So that I'm not so sure if we're going to see that. A lot of that depends on exactly how far away the moon is from the Earth. Eric mentioned earlier the partial eclipse, or there's an annular eclipse as another type. What we're going to see right now, this time, is a total solar eclipse, where the moon is going to pass at a distance from the Earth and between the Earth and the sun, where the moon will completely block out sunlight. An annular eclipse, on the other hand, is where the moon is closer to the Earth than it otherwise normally would be, and there's a little bit of sunlight around it. So my guess is that we're not going to see that effect, but I could be wrong, because I think the moon is going to completely block out the sun.
Right. So indeed, this is a total solar eclipse, not an annular eclipse.
Yes.
And Right, and Blago in the chat has just corrected me. Thank you. Diamond ring is just as if there happens to be a valley at the point of first or last contact, and that makes perfect sense, of course. As you mentioned, Chris, that the Earth is not that the Moon is not a perfect circle. It has features. It has mountains and valleys and so on. So if you've got a little valley or a surface feature there, it's going to let the sunlight through. And if that happens at the point of contact or exit there, then the sun is going to shine through and you'll get that diamond ring effect.
Right.
Okay, is there anything that you guys would like to add? I'll look at winding the Hangout up shortly. If there are any other questions in the chat that people would like to ask finally. Can you see the chat now?
We can, yeah.
We can, yes, we have it.
Okay.
My eyes.
So it's been a very...
I'd have to get way up to read
Sorry,
it.
Chris, go ahead. What was that, Chris?
Oh, nothing. I can't really read it because of my eyes, but Eric can.
Yes, I've been reading it and trying to relay information to Chris. So, but the one thing I'd like to add is, final thoughts, I guess, are about this hypothetical brown dwarf in our solar system, and how unrealistic this idea is. And if you actually use some logical thinking, and you have a couple of astronomers like Chris and myself, and your network of astronomers, if it was out there, we would see it, and I could definitively tell your viewers that there's no chance that it is. And if somebody comes up with some coordinates for it, I'd be more than happy to offer some of our telescope time to look for it. I'm up there almost every night anyway, and it'd be kind of fun to try to find this. I can tell you that we wouldn't. I mean, you would see it. It would be the brightest Jupiter in the night sky, very bright. But I'm up for the challenge. So if there's anybody out there with an RA index or altitude azimuth coordinates for the brown dwarf, I'd be more than happy to check, and I'd be more than happy to make available any data that we collect while trying to attempt to find one.
Absolutely, thank you. Now, just some final comments too about viewing the solar eclipse. Of course, people should never try to view the eclipse without eye protection. You need to use a proper solar viewer. You can buy these online. There we go, something like that. That's what you need to use. At the very least, and I should really recommend proper viewers like the ones that Eric has just shown there.
Sure, I can hold it.
Yeah, there we go. You can order that sort of thing online. Is there anywhere else you would suggest that people could get these from, Eric?
Check your local library. Check your local amateur astronomy group. A lot of organizations are giving them away for free in large amounts to places like that to hand out to the public. So
right.
Definitely check there first. But if not, if you do need to order them, I know that there are a lot of telescope manufacturers that are selling them pretty cheap. I'm sure if you go to a place like Amazon or something like that, you can find them for. They should be very cheap. If people are charging you a lot of money for them, then you're getting ripped off. So
I don't know if people can read what I'm holding up, but there's a contact info for the ones we got for our physics department. My hand's
right.
kind of.
It's backwards.
Oh, it is. Well, if you can read backwards or hold a mirror up to this, there.
Yeah,
I'll just. I can, if you don't mind, could I read their phone number off, or their company?
Absolutely.
So it's Eclipse shades. They're manufactured by the Rainbow Symphony Company out of Reseda, California, and their phone number is area codes 818-708-8400, and their website is www.rainbowsymphony.com. And they're very inexpensive. Yeah, we buy these by the bulk. We bought these by the 500s, and I don't remember what we spent, but they're very inexpensive.
You can also make them if you don't mind doing a little do-it-yourself stuff with just some sheets of Mylar.
Yep.
Or if you don't want to do that, just buy them.
Right. Now, the other thing that you can get away with using is that if you go to your local hardware or engineering supply store, you can buy replacement welding lenses. Now, you would want to have at least a number 12, preferably darker, a 14. A number 14 would be ideal. The welding lenses do come in different qualities as well. So if you get the opportunity to ask if you could take the lens outside and check the sun with it, obviously ask so they know that you're not stealing them. You don't want to get yourself arrested. But some of them have a more opaque quality, and some of them have a sharper, clearer image. The other option would be to use an electronic welding lens, which will auto adjust for brightness. I've sort of had a bit of a play with that. But ideally, you really want to use a proper solar viewer like the ones that Eric was showing there. And just go back to an earlier question. Mark Hale said the hobby shop did not sell sun filter for my telescope. They said it's unsafe. Now, just to clarify on that point, there are different types of sun filters for telescopes. There are some that actually screw onto the eyepiece. Now, these are very dangerous and they should not be used, as well as problems of the heat coming through the tube of the telescope, which can actually damage the internals of the telescope and the eyepiece as well. The actual sun filter, the screw-on sun filter on the eyepiece, can potentially crack in the heat. And of course, if that happens when you're looking through it, then you're going to be instantly blinded. The other type of sun filter for telescopes is one that actually goes on the object end of the telescope. So that's the end that's looking at the sun. So whether you're using a refractor or a reflector, you can actually fit a sun filter, such as a beta solar filter, over the end of the aperture. Now, normally the aperture in these beta solar filters is actually much smaller too than the aperture of a large telescope. That's why I was saying in my first Hangout that there would be no advantage in me going down to the observatory and using the 14-inch telescope, because the beta solar filter that we put on the end of it has an aperture, I think, of about maybe 3 inches diameter, something like that.
I think we're going to be full aperture.
Yeah, that's exactly what we're going to do.
Yeah. Okay, so if we've got nothing else to add on that, I think I'll wind up the Hangout. And thank you, Eric, and thank you, Chris, for joining me. It's been a pleasure. It's been some very interesting discussion there. And thank you to everyone in the chat. And we look forward to having another Hangout and you joining us there again. So this is Dazzathecameraman, and thank you for joining me.
Thanks.
Thanks.
Thank you, guys.